Okay, let's see if we are live.
I think we are live.
Okay, so let me share my screen and are you seeing the slideshow mode?
Yes.
Okay. Thanks, Mohammed. So good morning to everyone. Welcome to today's meeting of P&S course of on modern SSDs. Today I'll be discussing a recent work of our group, which is called Flash Cosmos, in flash bulk bitwise operations using inherent computation capability of NAND flash memory. This was a work that was published at Micro 2022. And it's a very relevant topic to and a new research direction in storage systems. So I'd like to go through this work and present it to all of you. So let's quickly jump to the sorry. Just a moment. Sorry. So let's quickly jump to the executive summary. So so the background of this work is that bulk bitwise operations are widely used in many modern data-intensive applications. These applications can be databases, graph processing, or cryptography. What I mean by bulk bitwise operations is the bitwise operations that we perform between two operands, let's say bitwise AND, bitwise OR, bitwise XOR, and so on. So these are fundamentally there in all kinds of applications in modern computing systems. So so why do we need this work of called Flash Cosmos? So the problem that these bulk bitwise operations are experiencing is they are bottlenecked by two key problems. One is the data movement between the storage and the compute unit in traditional systems and in storage processing systems. So these operands or the data on which these bulk bitwise operations are performed are typically stored in the storage system like an SSD. And whenever the computation has to be performed, it is brought to the compute unit, which is a CPU or a GPU. And then the computation is performed and it's moved back to the storage system. So there is a lot of data movement which affects the performance and the energy efficiency of bulk bitwise operations. And if we go to some of the state-of-the-art approaches in bulk bitwise operation computation, we see that even when the computation is moved to, let's say, a storage system, the data sensing or reading the operands one by one is a bottleneck for performance and efficiency. While the data movement is a key bottleneck, there is also another aspect, which is the reliability of these operations. Considering that modern NAND flash memory is very highly error prone, and it uses a lot of mechanisms to make the flash memory error tolerant. These techniques have to be highly reliable. So some of these prior approaches are not very reliable, and the applications needs to be error tolerant to use these techniques. So our goal is to improve the efficiency, improve the performance, energy efficiency, and reliability of bulk bitwise operations in flash processing. And to this end, we propose Flash Cosmos, which is flash computation with one-shot multi-operand sensing, which is an in-flash processing technique that is based on two key ideas. One, the first idea is called multi-wordline sensing, where we enable reading of multiple operands with a single read operation. And the second idea is enhanced SLC mode programming, which increases the voltage margin between the two states in an SLC flash memory. And this, by increasing the voltage margin, we get a higher reliability during in-flash computation. So just to discuss some key results, we evaluate Flash Cosmos using 160 real 3D NAND flash chips. And we do a system level evaluation using a state-of-the-art SSD simulator on 3 real-world workloads. And Flash Cosmos improves the performance and energy efficiency by 3.5x and 3.3x over the state-of-the-art in-flash processing technique, while it also provides very high reliability during computation. So this is the executive summary. Let's quickly jump into and see what is the agenda for today's talk. So we first go over the motivation. So I briefly explained why we need Flash Cosmos. We'll provide some information on why, what is the motivation for our work. Then we go into a bit of background where we discuss some background on the NAND flash memory and how NAND flash memory can inherently support these bulk bitwise operations. And then we look into the key ideas of Flash Cosmos. And we'll briefly discuss the evaluation and then provide a summary of our work. So, so moving into motivation, so bulk bitwise operations are present in all kinds of applications that we use in our daily lives. We use databases, web search, genome analysis, graph processing, set operations, cryptography, and hyperdimensional computing. So all these applications have, and a lot more applications have these bulk bitwise operations. But the key challenge of these operations or these bulk bitwise operations is that the data movement between the compute units and the memory hierarchy. As I mentioned, the data has to be moved from the storage system where the data is stored all through the memory hierarchy, which includes the main memory and the host, the CPU or the GPU, and the computation is performed, and then the data is stored back in the storage system. So this is this data movement affects the performance of the bulk bitwise operations. So what is this data movement bottleneck that we are that I am telling all the time? So we look at how these operations are performed on a typical system where which we call outside storage processing. And here in this system we have a host CPU, host processor, which is a CPU or a GPU, and then we have the main memory and the storage system. So these are connected using the different interconnects that we use in our typical system. So, so when we have to perform these bulk bitwise operations, the data is read from the storage to the storage system to the main memory. And then the host processor reads it from the main memory and performs the computation within the registers. And then once the computation is performed, it writes back the result to the main memory, and from there to the storage system. So this is what is happening in the typical system, which we call outside storage processing. The key bottleneck here is that the bandwidth of the external bandwidth of the storage system, which is around 8 gigabytes per second, remains a key bottleneck when you compare it to, let's say, the bandwidth that is present between the host processor and the main memory, which is between tens to hundreds of Gbps. So compared to the main memory bandwidth, we have a limited bandwidth in the external between the storage system and the main memory. So the amount of data that can be transferred in parallel is less. So this is a data movement bottleneck. So the external I/O bandwidth is the key bottleneck here. So how do we improve this situation? Near data processing is a mechanism which we adopt in such cases where we move the computation closer to where the data resides. So if we look at some of the prior works in near data processing, we see that um, at cache level, we have a prior work called compute cache. And then when performing computation within the DRAM based main memory, we have Ambit. This is a work from Safari Research Group. And then we also have Pinatubo, where we perform computations within the NVM based main memory. We also have a prior work called Biscuit, which performs in storage processing, which means that the computation is performed within the SSD using the SSD controller or the embedded cores available in the SSD. And then we also have in-flash processing, which is where the recent prior work called Parabit, which performs computation within the flash chips. So we are mostly concerned about in-storage and in-flash processing in this work, because here we cannot fit these two works are relevant because we have large data sets in bulk bitwise where we perform bulk bitwise operations, and these data sets do not fit into the main memory. So this is our focus area for this work. So let's look at these two areas. One is the first one is in storage processing, where we perform the computation using the in storage computation unit within the SSD. These computation units are typically embedded cores or FPGA, and ISP reduces the external data movement compared to outside storage processing. This is done by transferring only the computation results to the host. So let's look at a similar figure like we saw earlier, where we have a host processor, the main memory, and the storage unit, but we see the internals of a storage unit, which is where we have a in-storage computation unit and several NAND flash chips connected to this unit using shared channels. So the idea of in-storage processing is we read the operands from the NAND flash chips to the in-storage computation unit, and the computation happens within the SSD, and only the result, which is much less in size than the operands themselves, or maybe equal to the size of one operand, we transfer only the result to the host processor. And if we see what if we see what is the bottleneck of this kind of an approach, we see that the reads have to be done over these shared channels, which where the typical bandwidth is around 9.6 Gbps. So if we are performing within the SSD, then the bottleneck is the internal bandwidth of the SSD. So that is the main bottleneck in ISP. Now we look at in-flash processing, where we improve this further and move the computation to where the data actually resides, which is the NAND flash chips. So IFP performs computation within the flash chips as the data operands are being read serially. And IFP reduces the internal data movement bottleneck by transferring only the computation results to the in-storage computation unit. So if we look at the same figure that we saw earlier, we perform the computation within the NAND flash chips, and then move only the result to the in-storage computation unit, and even to the host system. So this is a much more improved situation compared to outside storage processing and in-storage processing. But even here, there is a bottleneck, which is the serial data sensing, which means that if we look at prior works, the computation is performed while we serially read the data from each flash page in a block. So this remains a bottleneck. So because read is a very costly operation in NAND flash memory based devices, so we think that data sensing is a key bottleneck in this in flash processing. So let's take an example. Let's look at what is the data sensing that is happening in flash processing. So a state-of-the-art IFP technique, which is called parabit, performs bulk bitwise operations by controlling the latching circuit of the page buffer. So in each flash block, we have a, or in each flash chip, we have a page buffer where the data actually is transferred within the flash chip and then moved to the moved outside to the outside the flash chip. So if we look at a NAND flash chip, we see several pages and a page buffer in the NAND flash chip. So typically we store each operand of a bulk bitwise operation within these NAND flash chips. So let's say we consider 4 operands here and we store them in different pages. So in this state-of-the-art approach, we perform the operation, we perform these bulk bitwise operations by performing data sensing, and this is done one after the other. So when we read A and then read B, we get a bulk bitwise or bitwise AND of A and B, and next we read C and we get bitwise operation of these 3 operands, and so on. So if there are hundreds of operands or thousands of operands, we need to kind of read each operand at a time, and the result gets accumulated in the page buffer. So this is an expensive operation because we need to perform 1,000 reads if there are 1,000 operands. So this is the data sensing bottleneck that we see in flash processing techniques. Now, this is not the only challenge in flash processing. We also see that there are reliability issues because NAND flash memory itself is very highly error prone substrate. So there are many sources of disturbances in NAND flash memory which cause data corruption when stored in NAND flash chips, or when we perform a program or a read, it can cause some bit flips. So to avoid this kind of data disturbance, we in NAND flash memory, typically we use ECC and data randomization techniques to make it more reliable, make the operations more reliable. And these techniques, reliability techniques, cannot be used by these prior IFP approaches or any IFP approach, because these techniques are the computation is performed within the flash chips, and these techniques are not available in the flash chip itself. So let's look at a figure to see why this happens. So we see the flash chips connected to different channels, and we see the ECC engine, which is helpful in making the data reliable, and also the scrambler, which is used for randomization technique. These 2 components are within the SSD controller and outside these NAND flash chips. So when we have to make the operation more reliable, we need to transfer the data from the flash chips to the ECC engine and the scrambler to randomize to do error correction and data randomization, and then move back the data to the NAND flash chip. So there is again a bottleneck here, because we need to keep moving the data back and forth between the flash chips and the SSD controller. And then this kind of voids the advantages that we get from performing computation within the flash chip. So, but the other point is to also see why we cannot put these things in these flash chips themselves, because these components are very expensive, and they are power hungry. So it's difficult, and there are also hundreds of, let's say, tens of flash chips within the SSD. So we can't put these components in each flash chip. So how do these prior approaches work? So let's say without the ECC and randomization techniques, the data may have some error bits which we indicate with this X mark, and so when we perform the computation or through data sensing, these errors actually persist in the result, and this situation is not good. So this means that these IFP techniques require the application to be highly error tolerant, and so this is a key limitation of these prior works. So considering these two limitations of data movement and reliability, our goal is to address the bottleneck of state-of-the-art IFP techniques, which is where we perform serial sensing of operands. And we also want to make IFP more reliable by providing accurate computation results. So let's look at a glimpse of how our proposal looks. So in Flash Cosmos, we enable computation on multiple operands using a single sensing operation. And we also, Flash Cosmos also provides high reliability during in-flash computation. So if we look at the same flash chip where we have operands stored in different flash pages, in Flash Cosmos, the computation happens in this fashion. So we read all the operands simultaneously, and this results in the bitwise the result of the bitwise operation accumulated in the page buffer at one shot. So this is considerably better compared to some of the prior approaches, because there we perform the computation by doing this data sensing in a serial manner. So so this is the motivation for our work. Any questions so far before we jump to background? Okay, so let's look at the background now. Here in the background section, I will quickly discuss some aspects of some basic aspects of NAND flash memory, and then how NAND flash memory can inherently support these bitwise operations. So let's look at a single flash cell. So a NAND flash cell stores data by adjusting the amount of charge in a cell. So an array cell doesn't have any charge, and or it has very low charge level, and an array cell indicates the value 1, and a programmed cell has high charge level, and in NAND flash memory it indicates a value 0. And when we activate these two, when we activate cells, either it could be array cell or a programmed cell, when the array cell acts as a resistor, and the programmed cell operates as an open switch. So this is the key principle behind NAND flash memory, and how it behaves when we activate a flash cell. So let's look at a NAND flash string where we serially connect many flash cells, and as you can see, these different flash cells are connected serially, and they are connected to a bit line. So this NAND string is also connected to a sense amplifier at the end, which will detect what is the value that is available in the NAND flash string. So when we so let's say there are some non-target cells where which we don't want to read as part of a read operation, then these non-target cells operate as resistors regardless of the stored data. So because of the high pass-through voltage that we provide to these flash cells. Now, if we have a cell that we want to read, and currently it is in array state, then it acts as a resistor. And when we perform a bit read operation, the bitline current that flows through the NAND string is detected as a 1 because the current can flow through the NAND string because all of these cells operate as resistors. And the sense amplifier detects it as a value 1. In the other case, when this cell operates as an open switch, or it is in a programmed state, when the bitline current flows through the NAND string, the sense amplifier reads it as a 0 because the bitline current cannot flow through the NAND string as the programmed cell operates as an open switch. So this is the key idea behind the flash cell and the read mechanism. So now let's look at a NAND flash block. So a NAND flash block is typically comprised of multiple bit lines which are basically laid out next to each other. So there are maybe hundreds of bit lines connected to different cells, and this forms a NAND flash block. The cells within basically the encapsulation of all these flash cells forms a NAND flash block, and we also see this thing called word line where these flash cells are connected in a horizontal manner so that we can operate these flash cells at the same time. So these word lines typically form the page that we talk about in NAND flash memory, which we saw earlier also, where we stored all the operands. So these word lines form the pages in flash memory. So a single word line controls a large number of flash cells, and it provides high bit level parallelism. And so if we look at different blocks, let's say we have hundreds of blocks in a flash chip, we see that there is some parallel between the way these NAND flash blocks are designed, or the architecture of these NAND flash blocks, the cells within the NAND flash blocks, with a digital AND logic. We see an example of a 2-input NAND logic where we have the operands or the transistors connected in series, and we get the output here. So we see similarity between the way the cells are connected in the NAND string and the digital AND circuit, 2-input AND circuit. And similarly, we also see a similarity with digital OR, where if you see across these different blocks, if we look at the flash cells, we can see a similarity between with 2-input OR logic. So this is a key idea or a key insight that we take while developing Flash Cosmos. So this is a brief background on how NAND flash memory works, and then and how inherently we can support bitwise operations within the flash memory. So any questions till now? Okay, let's move on to the key idea of Flash Cosmos. So Flash Cosmos enables in-flash bulk bitwise operations on multiple operands with a single sensing operation. And we call this technique multi-word line sensing. So let's look at what multi-word line sensing is. So we have two types of multi-word line sensing. One is called, the first one is called intra-block MWS, where we simultaneously activate multiple word lines within the same block. So we perform using the intra-block MWS, we perform the bitwise AND of the stored data in the word lines within the same block. So let's look at an example. So we have, let's say, 4 word lines here, and word line 3 and word line 4 are non-target cells, which means that we don't want to read them, and these operate as resistors because of the high pass-through voltage that we provide to these cells. Now, depending on the state of the cell, either if it's programmed or erased, they act as open switches or resistors. And when we simultaneously read all the bit lines, or pass bit line current through all these bit lines, and we simultaneously activate these word lines also, we see that the bit line current passes through the NAND string only if all the cells act as resistors. So a bit line reads as 1 only when all the target cells store 1. So this is equivalent to the bitwise AND of target cells. So all these flash cells represent 1, and the result would also be a 1. Now we look at an example where all 4 word lines are target cells, and we simultaneously activate these word lines at the same time. And we see that even if there is a single open switch or a programmed state, a cell with in a programmed state, the current cannot pass through the NAND string, and it represents a 0. So this is also very this is another case of the bitwise AND logic, where even if there is a single 0 in the operands, then we get a 0 as the result. So this is a simple explanation of intra-block MWS. So this intra-block MWS enables bitwise AND of multiple pages in the same block using a single sensing operation. Now let's look at how we can perform simultaneous activation of word lines across different blocks. And this we call it as inter-block MWS, where we activate multiple word lines in different blocks. And this helps us in performing bitwise OR operation of the stored data in the word lines. So here we have 2 blocks, and we look at 1 word line in each block. So when we send the bitline current through these NAND strings in different blocks, because since these NAND strings are connected to the sense amplifier, the NAND string in each block is connected to a sense amplifier. Even if there is one open switch connected in, let's say, in a block, if there is a resistor in the other block, the result would still be 1, because the current would still be passing through the NAND string. So this is an example of the bitwise OR. This is how the OR operation works. So even if there is one operand which is a 1, the result would be the value. So if we need to get a 0, then it means that both the cells that we are activating at the same time needs to be open switches. So this is equivalent to the bitwise OR. And we look at the case when we get 1 as the result. And here we see that even if there is a single cell which operates as a resistor, then we get the value as 1. So using the interblock MWS, we can perform bitwise OR of multiple pages in different blocks using a single sensing operation. So now we have looked at how we can enable bitwise OR and bitwise AND in a flash chip. Now we look at how we can perform other operations. So Flash Cosmos can also support other operations like bitwise NOT, This is done using by exploiting the inverse read operation, which is already supported in modern NAND flash memory for copyback operations. So inverse read is already supported. Then we also use to perform bitwise NAND or bitwise NOR. We use inverse read operation with bitwise and bitwise OR operations. So this is typical of how we get NAND or NOR using and OR operation. And then we also can also perform bitwise XOR and XNOR. This is done using the XOR operation, which is already supported between, let's say, the cache latch and the sensing latch. And this is a feature which is already supported in the NAND flash memory. So using these features, which is supported inherently in the NAND flash memory, we can also perform other operations, other bitwise operations in Flash Cosmos. So this is a brief overview of how we can perform bulk bitwise operations on multiple operands using a single sensing operation with a single sensing operation. And now we look at how we can increase the reliability of these in-flash bulk bitwise operations. And we propose a technique called enhanced SLC mode programming. So let's look at enhanced SLC mode programming now. So SLC mode programming provides a large voltage margin between the erased and the programmed states. So if this is a distribution of cells in an SLC word line, so basically some cells are in the array state and some cells are in the programmed state, and there is a large margin, voltage margin between the two states. So so we can read these cells without even if there is a slight disturbance caused by read disturb or program interference or any error source. So this large voltage margin provides some reliability in the SLC mode programming. But this voltage margin is not large enough because we do not use ECC and data randomization techniques. So without those two reliability techniques, we are still very highly error prone when it comes to SLC mode programming, and we need to address this while performing in flash computation. So enhanced SLC mode programming increases the voltage margin between the two states, between the erased and the programmed state, and basically the programmed state would be much the threshold voltage of the programmed cells would be much higher. So a wider voltage margin between the two states improves the reliability by making the cells less vulnerable to errors. And this is done by performing additional steps in the incremental step pulse programming, or the ISPP process, which is used during the program operation. And this increases the voltage margin and makes the program state more narrower, the distribution of cells in the program state. So this wider voltage margin can negate any disturbance that is caused that can cause errors, and we can perform a read operation without error bits. So this is the idea of enhanced SLC mode programming. And ESP improves the reliability of in-flash computation without the use of ECC or data randomization techniques. And ESP can also improve the reliability of prior in-flash processing techniques as well. So increasing the voltage margin can increase the reliability. So so now that we have looked at the two key techniques, the multi-wordline sensing and the enhanced SLC mode programming, we look at what are the new flash commands that we propose in this work to enable more in-flash bulk bitwise operations, or provide a system support to perform bulk bitwise operations in flash. So we introduced 3 new NAND commands to support Flash Cosmos. One is called the MWS, which is the multi-word to enable multi-word line sensing. And then we also have ESP, which is to perform enhanced SLC-Mode programming. And we also need to we introduce another command to perform XOR operation. So let's look at what MWS command is used for. As I mentioned, it's used for MWS operations, both intra and interblock multi-word line sensing. Then we also use this for performing inverse read operation, and also accumulation of results of all the reads. So we'll see an example soon of how these commands are used in an example. So we also introduced another command slot along with MWS called ISCM, which allows the flash controller to turn on or off 4 different features. So we can, with ISCM, we can enable or disable the inverse read mode, and we can also initialize the sensing latch and the cache latch, and the data movement between the sensing latch and the cache latch. So for MWS, we also introduce a page bitmap to specify which word lines have to be activated for MWS operations. And we also allow 4 address slots for interblock MWS command. So this address slot that you are looking at can be, we can support up to 4 different addresses, which means that we can read 4 different blocks at the same time. Word lines in 4 different blocks. So this is this is about the MWS operation or the command slot. Then we look at ESP command, which works very similar to a program operation, just that it increases the number of steps in the incremental step pulse programming, and increases the voltage margin between the erased and the program states. Next, we also support XOR command, which performs bitwise operation between the sensing and the cache latch and stores the result in the cache latch. So these 3 new NAND commands can help support Flash Cosmos at a system level. And we see an example next on how these 3 commands are used in this example. So let's look at this equation, which is a bitwise, where we perform a lot of bitwise AND and bitwise OR operations. So we first look at, we break this equation into 2 parts. One where we take the C1 bitwise OR with C3, and then D2 bitwise OR with D4, and then we do a bitwise AND of these 2 of the results of these 2 operations. So we take this first, and then we accumulate the results of this operation with the first part. So we look at C1 bitwise OR with C3 and D2 bitwise OR with D4. One thing that we do in Flash Cosmos is to try to utilize bitwise AND operations more frequently, which means that we use more intra block MWS operation. So to do that, we basically convert this part of the equation into bitwise AND operations. So to do this, we need to make C1 bitwise OR with C3. We need to if we need to use bitwise AND, then we need to store the inverse value of C1 and C3, and similarly with D2 and D4. So if we look at the way these operands are stored, we store the inverse value of C in block 3 and D in block 4. So we can perform the computation of this part of the equation using one MWS operation, where we say indicate the different blocks that where the operands are stored to perform the interblock MWS, and the different word lines to indicate which are the word lines within the same block where the computation needs to be performed. So we see block 3, which is indicated by this bitmap where for C, and then block 4 for the operand D. And the page bitmap indicates which pages are part of these are to be considered in each block. So 1 and 3 are the pages which needs to be read for this computation, and 2 and 4 for in block D. Now we also look at this ISCM command slot, and we see that the inverse read mode is enabled. And then since this is the first step of the operation, we initialize the cache latch and the sensing latch. And then we also enable the data movement between the sensing latch and the cache latch, or the data copy. So this part basically enables the first part, computes the second part of the equation. Now, if we look at the first part, then we see that the operand A is stored in block 1, and operand B1, B2, B3, operands B1, B2, B3, and B4 are stored in block 2. And since there are more bitwise AND operations that we perform in block 2, we use this as we consider this part of the equation as is and don't use inverse operation. So we see that again we have to perform this MWS on 2 blocks. So A1 is for A1 we use block 1 and word line 1, and for B the operands in block 2, we provide the block information and all the word lines within that block. And if you look at the ISCM command, we see that inverse mode is not enabled, and we also don't enable the initialization of cache and sensing latch, because the cache and sensing latch already have the partial output for the first step of the operation. And then we also perform the data copy here to move the data to the cache latch. So this is how we structure the bitwise operation in Flash Cosmos. So this is basically what I explained just now, and we do it with we compute this equation using 2 MWS operations. And so at the end of at the second step, we get the accumulation of both these MWS operations, the result of both these operations, and that will be the end result. And I forgot to mention that why we prioritize bitwise AND operations more. That is because the bitwise AND operation consumes less power in NAND flash chips compared to bitwise OR, which is reading across different blocks. So that is the reason why we prioritize bitwise AND. So that's about the key mechanisms that we have in Flash Cosmos. Any questions till now? Okay. Now we'll quickly jump into the evaluation of this work. The evaluation methodology we use is has 2 approaches. One is we use 160 real state-of-the-art 3D NAND flash chips to evaluate the feasibility of Flash Cosmos. So we perform this real device characterization to validate the feasibility, performance, and reliability of Flash Cosmos. And we do it on 160 48 layer 3D TLC NAND flash chips. which means that it's triple level cell, and each block has 48 word lines. So we use 160 different 3D NAND flash chips, and the number of word lines that we have tested is approximately 3.5 million word lines. And these word lines are the Flash Cosmos is tested under worst case operating conditions, which means that we check the feasibility at 1 year retention at 10 kp cycles, which means that we write the data and then keep the device or the flash chips. Don't read the flash chips for 1 year, which is the key principle behind retention time. And all this happens at 10 kp cycles, which means that 10,000 program and erase cycles have already been done on the block. And we use worst case data patterns while programming to test the feasibility and the reliability of these operations. So the results of this real device characterization shows us that both intra and inter-block MWS operations require no changes to the cell array of commodity NAND flash chips. And both MWS operations can activate multiple word lines. In case of intra-block, we do up to 48 word lines, and in case of inter-block, which is across different blocks, we can do simultaneous sensing of 4 word lines in each block. And this comes at a small increase in sensing latency of less than 10%. And ESP significantly improves the reliability of computation results, and we achieve almost 0-bit error in the tested flash cells. Now, this is about the real device characterization to check the feasibility, performance, and reliability of Flash Cosmos. To test the performance and energy efficiency of Flash Cosmos, or at a system level, we use 3 real-world applications that perform bulk bitwise operations. And to do this, we use a state-of-the-art simulator called MQSim to model the performance of Flash Cosmos and the baselines. And we use 3 real-world applications. One is bitmap indices, which is a database application. Then we also have image segmentation, which is an image processing kernel. And then k-clique star listing, which is a graph processing kernel. So BMI typically has a bitwise AND, which performs a bitwise AND of up to 1,000 operands. In image segmentation, we have bitwise AND of 3 operands, but these operands are quite large, up to 44 gigabyte. And k-clique star, the workload performs both bitwise AND and bitwise OR operation of up to 32 operands. So what are the baselines that we are considering for this evaluation? The first one is the outside storage processing, which is where we move the data to the compute units in the host, and we model a multi-core CPU, which is Intel i7, for this baseline. And in storage processing, where is another baseline where we perform the computation in the embedded cores within the SSD. And this is for this we use an in-storage hardware accelerator. And then for Parabit, which is a state-of-the-art IFP mechanism, we model Parabit in the simulator. So when we look at the performance and energy efficiency, we show the performance in terms of speed up over OSP, which is outside storage processing. And we show different workloads here. And the y-axis shows the speed up in log scale. And we see that we show the same workloads in energy efficiency also, and this is the y-axis is showing the energy benefit over OSP. So Flash Cosmos provides significant performance and energy benefits over all the baselines. You can see the bars in green, which is indicating more speed up and more energy efficiency compared to the baselines. And the performance and energy benefits only increase with the number of operands. So if we have more number of operands stored in a flash block, and we can perform simultaneous read operation or multi-wordline sensing of these operands, then the benefits only increase compared to other approaches. So this is a brief explanation of results of Flash Cosmos. We have a lot more results in the paper, and I would highly encourage everyone to go through the paper. This is the archive link for that. So that's the evaluation and the key results of Flash Cosmos. Any questions till now? Okay. So now coming to this end of the presentation, I will summarize what we have gone through in Flash Cosmos. So Flash Cosmos is the first work to enable multi-operand bulk bitwise operations with a single sensing operation, while providing high reliability for the computation results. Flash Cosmos improves the performance by 3.5 times, 25 times, and 32 times on average over Parabit, ISP, and OSP. And Flash Cosmos also improves energy efficiency by up to 95 times over OSP. And the benefits of Flash Cosmos come at a very low cost, and it requires no changes to the flash cell arrays. So these are the key points of Flash Cosmos. As I said, I would encourage everyone to go through the paper, and we have more results and analysis and insights in the paper. So that marks the end of my presentation. If there are any questions, we can take it up now.
Thanks a lot, Rakesh, for your presentation.
Thanks. Okay. Looks like there are no questions on YouTube as well. We can, Mohammed, let me stop the live streaming.
I think if you close the Zoom. Yeah, true. You need to stop the Zoom. Sure.
Okay. Let me stop my share and